solving trig equations. So we've looked at trigonometric identities and we've manipulated them and looked at expressions and looked at verifying them. Now we're going to use what we know to solve trig equations. So when we're solving for a trig value, an angle value. So for example, I have cosine of theta plus 1 equals 0. So this is a pretty simple one. I don't have to manipulate it too much, and I'm going to solve it much like I would solve an algebraic equation. So subtracting 1 from both sides, and I have cosine of theta equals negative 1. So I'm wondering what angle, when I take the cosine of it, am I going to get negative 1? Now I can look at this in a couple of ways. I can look at this on the unit circle. So if I look at the unit circle, I can see that at 180 degrees, I am at the point negative 1, comma 0. So my x value, since it's a unit circle, is negative 1, and I know that my cosine is negative 1 at that point. 180 degrees, or if I wanted to think in radians, pi radians. However, if I went around the circle again, so I took that 180 degrees, and I added 360 degrees, I would get right back to that negative 1, and cosine would be negative 1 there too. Conversely, if I subtracted 360 degrees, I would be back there as well. So I have infinitely many solutions. Let's see how our graph illustrates this. So if I have the graph, I graphed y equals cosine of theta here. So this x-axis would be theta, and my y-axis would just be the value of the cosine of theta. So I can see over here at pi, I am at negative 1 on my y-axis. That's negative 1. And again, if I go a whole nother period, I'm back here at 3 pi, and I'm back here at negative 1. So then I go to 5 pi, and I have negative 1 again. I'm going to keep hitting this negative 1 infinitely. So this really has infinite solutions. However, sometimes it's constrained. So if I say I want the solutions between 0 and 360, or the solutions between 0 and 2 pi, if I'm thinking in radians, I only have one value for theta. Theta equals 180 degrees, or pi radians. But if I want to indicate the infinitely many solutions, if I don't have these constraints, I need a way to notate that. So if I take theta, and I start at 180 degrees, and I add multiples of 360, that means I'm just going around the circle again, and I'm ending right back where I started, all the way around that 360. Multiples of 360, I will have all of my solutions. So k can't be a fraction, it has to be an integer, and so it has to be positive or negative, or 0. So for example, our first solution, if k is 0, I just have 180 degrees, which is my first solution. If k is 1, I've gone one additional time around the circle. If k is negative 1, I've gone backwards one time around the circle. So this tells me all of my values as long as k is an integer. If I wanted to notate this in radians, I would start with pi, and I'm going to add multiples of 2 pi. So just going around that circle or going through the period again. So k times 2 pi. Let's look at another example, and this time we'll use some of our trig identities. So I have sine squared of x minus 1 equals cosine squared of x. And I do have a constraint here. X is between 0 and 360, I'll put or equal to, and 360. So when I see these squareds, I want to think in terms of probably my Pythagorean identity. Another trick is the wrong word, but another thing you need to think about when you're solving is it's helpful to have only sines or cosines. That's another helpful thought. So I'm going to take this cosine squared of x, and I'm going to write it in terms of sine squared of x. So I know sine squared of x plus cosine squared of x equals 1, because that's the equation for my unit circle, or any circle. And then I have cosine squared of x minus sine squared of x from both sides. Cosine squared of x equals 1 minus sine squared of x. So instead of the cosine squared of x, I'm going to put in 1 minus sine squared of x. Now notice that's different from the sine squared of x minus 1. I can't substitute this with cosine squared of x because my numbers are reversed. My 1's negative here and my sine is positive. If I wanted to take this side and put in a negative cosine of x. I could have done that, cosine squared of x, I could have done that as well, but I chose to do this because it was just a direct substitution. So then when I'm doing that, I'm going to go ahead and add sine squared of x to both sides here, and I have 2 sine squared of x, and then add 1 to both sides, 2. So I have sine squared of x equals 1. And then I'm going to take the square root of both sides, and so I have sine of x is equal to plus or minus 1. So I want to look where that occurs on my unit circle, and you could also use the graph if you wanted to instead. So where is sine positive 1? Sine's positive 1 up here at 90 degrees. Now if I wanted infinitely many solutions, I would have to add 2 pi times that k to this 90 degrees, but it's only asking me to find it between 0 and 360 degrees. So the other place I want to look at is when sine is equal to negative 1. Sine is equal to negative 1, my y value is negative 1 at 270 degrees, or 3 pi over 2 if you wanted radians, but we have it in degrees up here. And if I wanted infinitely many solutions, I would just have to add that 2 pi to it, times k, multiples of 2 pi, or multiples of 360. All right, so then let's look at something a little more complicated, and this will probably take you back to when we were doing quadratics. So I notice I have one that's squared right here, and I have one right here that's just to the first power. Now if you think in terms of x, which is kind of how we like to think about algebra, this looks like a factorable equation. It's got a squared term and it has 1 to the first power. So when you get a quadratic like that, this one's already set to 0, but it's easier to solve if you set it equal to 0. And here I have, instead of degrees, I have it in radians, and it is constrained. So I can factor this, and you can think about it as like 2x squared minus 3x minus 2 equals 0, where the x is equal to that sine of theta. So then I have 2 times the sine of theta and the sine of theta. So it'd be like 2x and then times x over, or x here and add 2x right here. So instead of x though, I have the sine of theta. So that's 2 and that's 1. And then I need to figure out how I'm going to multiply to get you this and to add to get you this, but I've got that additional coefficient. So I want to look at those outside and inside terms and make sure I get this negative 3. Well, I have a negative 2, so it's not too difficult. I know one's going to be positive, one's going to be negative. It happens to be this. I know it has to add to negative 3 when I multiply those outsides and insides. So I tried a negative 2 here and a 1, and if you wanted to go through the factoring by grouping, you could do that as well. But I know this negative 2 times this 2 is going to give me a negative 4, and then right here I'm just going to get a 1. And so I know I'm going to get to that negative 3. So I could multiply it out too and check my answer to make sure I got back to that. This is just another form, the factored form of this original equation. Now the reason I do that factoring is because now I can use the zero product property. I know if this is 0, the whole thing is 0. If this is 0, the whole thing is 0. So I can set each of these equal to 0 and solve. So let's look at this one over here. Sine of theta minus 2 equals 0. So add 2 to both sides, and I have sine of theta equals 2. Now if you think of the unit circle, or if you think of the graph, sine of theta is not going to give you 2. And so this here is not a solution. So it's a redundant solution. I mean, it's not a redundant solution. It's not a solution. It can't exist. Over here, if I'm solving, I subtract to 1 from both sides, and I get sine theta is equal to negative 1/2. So I want to know where on my unit circle sine of theta is equal to negative 1/2. What angle is that going to be? And I'm thinking in terms of radians. So I look at my circle and I go over here and I see I have a negative 1/2 here and a negative 1/2 here. They're going to be at the same height because we're talking about sine. So that happens at 7 pi over 6 and 11 pi over 6. And the way I figured that out is I labeled this as 6 pi over 6, which is just pi, to help me calculate which sixth it is here, and 12 pi over 6, which is the same as 2 pi. So then I look here, and I have negative 1/2, so that happens at 7 pi over 6 and 11 pi over 6. Now I have that constraint, so I don't have to add the multiple solutions. But let's look at one where we're adding multiple solutions to it. So here I have sine of 2x is equal to 2 cosine of x. So I want all values, and we're going to think in terms of radians this time. We could do radians or degrees, but in terms of radians, and I'm going to look at this and notice that I have that double angle. So from our double angle formula that we proved, I have sine of 2x is equal to 2 sine of x times cosine of x. So then I'm going to replace this sine of 2x with the 2 times sine of x times cosine of x is equal to 2 cosine of x. So when I'm solving this, you might be tempted to divide by cosine of x, but that will possibly make one of your solutions go away, because if cosine of x is equal to 0, then both of these sides will match. So in order to take that into account, you want to subtract this side and set it equal to 0. So if we just divide it by cosine of x, you can imagine cosine of x goes away, and then we're not taking into account where cosine of x is equal to 0. So whenever you have something like this and you have the possibility of dividing here, you have to be very careful and take into account that if that's 0, then that x is actually a solution. So 2 times sine of x cosine of x, subtracting 2 cosine of x from both sides, equals 0. And then I'm going to factor out a 2 cosine of x. I have that in both of these. So factoring is another technique that's going to let me use that zero product property. So I have 2 cosine of x times sine of x, that's what's left here, minus 1. Notice if I distribute that 2 cosine of x, I get back to that original one, equals 0. So this could be 0 or this could be 0. So 2 cosine of x equals 0. That happens when cosine of x equals 0. I can just divide by 2. And I can divide by that 2 because it's not a variable. If it's a number, that's okay. But if it's a variable, that takes us into kind of a tricky area. So then sine of x minus 1 equals 0. So I have 2 different possible solutions. Cosine of x equals 0. Sine of x adding a 1 to both sides equals 1. So cosine of x equals 0. So over here we have cosine of x equals 0 up here at pi over 2 and down here at 3 pi over 2. Sine of x equals 1 on one of those. So up here sine of x is equal to 1. So cosine of x equals 0 at pi over 2 and at 3 pi over 2. Sine of x equals 1 at pi over 2. So then I have here my x values. I start at pi over 2, and then I could go all the way around the circle again, and I would have that same value. So plus k times 2 pi, that's all the way around the circle, where k is an integer. I could go forwards or backwards. And then I also have x is equal to 3 pi over 2 plus k times 2 pi. Now this one right here also takes my sine of x equals 1 into account. But this extra one right here, x equals 3 pi over 2 plus k times 2 pi, I wouldn't have if I had divided both sides by that cosine of x. So this is the one with multiple solutions where k is an integer. If I had the constraint, I would just be looking at these 2 values.